The Story of a Wave by Carlos Roca. The equator is hotter than the poles as it receives a larger amount of solar radiation. This is because the sun rays are hitting straight downwards at the equator but at a highly oblique angle at the poles. As the surface in the equator is relatively hot, the surface air expands, becoming less dense than its surroundings. Through the process of convection, hot air rises, leaving a large gap, allowing air from the poles to come in and fill the gap. The air that rises from the equator is forced north and south until it gets denser and sinks back to the surface. A pattern is set up in each hemisphere. The Coriolis force takes effects on all large-scale movements, to the right in the north hemisphere and to the left in the south hemisphere. Instead of the air traveling all the way from the poles to the equator, it is divided in 6 spiraling wind bands, 3 in each hemisphere. Because the air latitude at 60 is continually rising, it reduces the surface pressure, explaining why the formation of low pressure systems would be ideal between 40 and 70. Because the air at 30 is always sinking, surface pressure increases, creating semi-permanent high pressure systems at around latitude 30. The Earth rotates around the Sun, inclined at an angle of 23.5 degrees. This angle is called obliquity of the ecliptic. Depending on which pole is closer to the Sun, one hemisphere is warmer than the other, except on equinoxes, where both hemispheres briefly receive the same amount of solar radiation. This has a massive effect on temperature variations between the pole and the equator between seasons. Because the temperature difference between the equator and the poles is higher in winter, convection cells work over time, producing more wind, deeper lows, and bigger surf in winter. Water has a greater specific heat capacity than land. Therefore, water takes a lot longer to warm up or cool down compared with the land. The difference in temperature between seasons is greater in land than in the ocean. As a result, land is warmer than the sea in summer, and the sea is warmer than the land in winter. Therefore, convection is greater in the land in summer and greater in the sea in winter. This creates summer patterns of low pressure on the land and high pressures on the sea, and vice versa in the winter. Because there is more land in the northern hemisphere than in the southern hemisphere, there is a greater variation of pressure, making the waves more consistent in the winter than in the summer. In the southern hemisphere, there is less variations due to the fact that there is less land. The waves are more consistent throughout the year. Coriolis force was discovered in the early 1900s by the French physicist Gustave Gaspard Coriolis. It is the reason why all large-scale motions turn right in the north hemisphere and left in the south hemisphere. The Earth rotates on its own axis from west to east, and it takes approximately 24 hours to do it. If you look at the lines of latitude, the equator is the biggest latitude line, and they get smaller as they get closer to the poles. Therefore, if you were in the equator, you would be covering more space than if you were at the poles on one of those 24-hour cycles. As a result, the equator moves faster than the poles as it has a larger distance to cover in the same amount of time. Storms are low-pressure systems surrounded by high-pressure systems that constantly want to fill in. Instead of the air coming straight from the high pressure to the low, the air is deflected by the Coriolis force, anti-clockwise in the north hemisphere and clockwise in the south. With high-pressure systems is the same principle, but the air tries to move outwards, but gets deflected clockwise in the north hemisphere and anti-clockwise in the southern hemisphere. Convection currents are caused when warm air rises and cold air sinks, creating an ongoing process. Currents found between the equator and the Cancer of Capricorn and tropic are called Hadley cells. Between latitude 60 and 90, the poles, we find polar cells. Between the Hadley and the polar cells, there are not major distinct convection cells. The polar front in the Atlantic, where the cold air from the north meets the warm air from the south, is where the low pressure systems tend to occur, found between Hadley cells and polar cells. Due to the temperature difference, a disturbance may happen, also known as a baroclinic instability, meaning there is a change in pressure of a distance causing the atmosphere to be locally unstable. This leads to a drop in surface pressure and high pressure cells try to fill up, being deflected by Coriolis. The low pressure systems travel in a cyclonic way, anti-clockwise in the north hemisphere. This front splits into two individual fronts, warm front and cold front. The warm sector is where the winds are blowing very strong and blowing in the same direction, ideal for the wave creation. On a weather chart, a low pressure system can be easily recognized as the isobars are very close together. Closer the isobars, greater the difference in pressure. Warm front is lower than the cold front, so the cold front will catch up with this warm front. This is called an occluded front. At this point, it starts to weaken. Anatomy of a wave. The amplitude, height of the water from its resting position. The height, distance from trough to crest, so double the amplitude. Period, time between one part of the wave and the exact same part of the next one passes an exact point. Wavelength, distance between one wave and the next one. Frequency, number of waves passing a point per second. In the mid-1950s, investigative work was underway by John W. Miles and Owen M. Phillips to investigate the physical mechanism behind wave generating. They came up with a theory that is still used today. The theory assumes that there are two basic mechanisms involved. The first one is producing small waves from flat sea, and the second one producing bigger waves from those existing small waves. Linear growth. The key to linear growth is that the air is not striking the surface of the ocean perfectly horizontally. It contains natural vertical fluctuations as well, causing it random wave motion. This produces capillary waves. Some of these capillary waves might be out of sync with the storm and therefore might die, but the ones that don't die are taken up to the exponential growth. At the exponential growth, these capillary waves are still receiving energy from the wind, so therefore they keep on growing and growing. Waves have limiting factors that stop them from growing into monster-sized waves. One of these factors is called as whitecapping. As the waves grow and grow and grow, at a certain point where the face of the wave gets too steep, and therefore the top part of the wave breaks. As the swell travels away from the storm center, it spreads out over a progressively wider area. This is because the movement of the water molecules is transmitted to the neighboring particles. Therefore, the wavefronts become ever wider, spreading the same amount of energy over a greater area. This spreading of the energy steals height from the waves. If the waves originated from a single point source, the width of the wavefront is approximately proportional to the distance it has traveled from the point. Normally, an energy reduction of a half equals a wave height reduction of 30%. Of course, real storms are not singular point sources of swell. In reality, the fetch itself can be quite wide. As a result, the spreading out of the wave front has less effect on energy reduction with distance. Waves do not carry water from one place to another. Waves are just messengers of energy. The motion of the particles in the surface is also transferred to the water below. Because of friction and energy loss between vertical levels in the sea surface, the orbits get smaller the further away from the surface. Another important property of swell is that it is not affected by the Coriolis force. Swell does not end because, unlike currents, swell doesn't carry any physical material from one place to another. It's just a message. In the deep ocean, any floating object, looked from the side, would trace a complete orbit every time a wave passed through, ending in the same spot after the wave has passed. The wave transmits energy, a message, from one part of the ocean to another, telling the particles in the surface to go round in circles. The main way in which the bathymetry affects a wave approaching the coast is by making it bend through the process of refraction. As the wave gets to shallower water, the orbitals from the wave start touching the seabed, slowing it down. As the orbital closest to the bed start to touch the bed, all orbitals lose energy and speed, and the wave slows down. The bigger the wavelength of the wave, the bigger the orbital, so it touches the seabed before a wave with a smaller wavelength. Refraction is the bending up of wavefront as it travels at different speeds over water at different depths. When one part of the wave slows down, the wave bends towards the slower part. There are two types of refractions, convex and concave refraction. Convex refraction is a point with shallow water either side of a deep bay, causes the wavefront to bow outward. Concave refraction is a shallow reef next to a deep channel, which means that the wavefront focuses most of its energy on the area of the reef, while the middle of the bay can be flat calm. A diffraction occurs when a wave passes an edge, passes through a narrow gap, or goes past an object. None of the properties of the waves are affected by diffraction. Diffraction is biggest when the gap equals the wavelength of the swell. The Erie-Barren number is a series of laboratory experiments to classify different breaker types according to the wave height, wave period, and beach slope. It classifies a wave between spilling, plunging, and surging, depending on its answer. Thank you very much for watching and listening.